Today, I would like to solve the following exercise using the induction principle on the natural numbers. As you already know, here we have the definition of the induction principle, and we are going to use it to prove this exercise. In this exercise, we have that for every n that is a natural number and that is greater and equal to 1, the following sum is going to hold. So we have that this sum is going to be equal to n squared. Since we want to prove this using this definition, we need to define our predicate. What is going to be our predicate? And when I say predicate, I mean our phi. In this case, our predicate is going to be the following one, this one here. This is our phi of n. Our phi of n is going to be that n is greater than or equal to 1 implies the following sum. We want to prove this using induction on n, as you can see here. Now, since we have all we need to do that, let's start. Our base, as you can see here, is going to be phi of 0. What is going to be phi of 0? Phi of 0 is just going to be 0 greater or equal than 1 implies the following sum. The sum from k equals 1 to 0 of 2k minus 1 equals to 0 squared. We have this statement, and we can notice that this statement has an implication in here. But we already know that a statement that has an implication, well, when we have an implication and the first part of that implication is false, it means that the whole statement is going to be true. And look what we have here. We have that 0 is greater or equal than 1. And this is false. False. But this is an implication. It means that this is false. The whole statement is going to be true. So the whole statement is true. Now look, we just proved that our base, that our base is true. Now, since we have that our base is true, we are going to continue with the inductive step. What is going to be our inductive step? As you can notice here in this definition, our inductive step is the one as follows. That's for every n, there is a natural number, phi of n implies phi of n plus 1. It means that this part that you can see here, we are going to assume that to be true. So we can write that in the following way. We assume that for every n belonging to the natural numbers, n greater or equal than 1 implies the following sum. We are going to assume this to be true. True. And this stuff here is our inductive hypothesis. Now, since we have that, we want to prove that if this is true, then phi of n plus 1 is going to be true. This is what we want to prove. Now, we need that for every n belonging to the natural numbers, m plus 1 greater or equal than 1 implies the following sum from k equals 1 to n plus 1 of 2k minus 1 equals to n plus 1 squared. We are going to prove this. Now we're assuming this. We're assuming that phi of n is true. And now we want to prove that phi of n plus 1 is going to hold as well. To do that, we need to study two cases. The first case is this one. First case. The first case is when n is equal to 0. What is going to happen? Look, we have n plus 1 greater or equal than 1. It means that we have 1 greater or equal than 1 because n is equal to 0. Now this implies the following sum from k equals 1 till 1 as well, because we have n plus 1. So this is going to be 1 of 2k minus 1 equal to 1 squared. Look, we have this sum. This sum is clearly equals to 1. Why? Because we can replace this k by 1. We have 2 times 1 minus 1. This is just going to be 1. This 1 squared is just 1, so this is equal. And we know this, that this is true, because 1 is greater or equal than 1. Well, it's equal to 1. Now, we can see that the whole statement is true. So for the case when n is equal to 0, the whole statement is true. Now, what happens when we take n greater or equal than 1? Second case. N greater or equal than 1. What we are going to have? We have that n plus 1 is greater or equal than 1 implies the following sum: k from 1 till n plus 1 of 2k minus 1 is equal to n plus 1 squared. And now in this case, we are going to use our inductive hypothesis, this one. We have that the sum from k equals 1 till n plus 1 of 2k minus 1 is going to be equal to the sum of k equals 1 till n of 2k minus 1 plus the last part of this sum. What is going to be the last part of this sum? It's just going to be n plus 1 equals k in here. It means that this is going to be plus 2 times n plus 1 minus 1. This is the last part of this sum. Now look, as I promised, we are going to use inductive hypothesis. And we can do that in here. Look, it's the same stuff that we have in here. It means that this is going to be equal to n squared. The whole thing is going to be equal to n squared plus 2n. We have 2 times 1 minus 1. This is going to be 1 plus 1. And we can factorize this part. And clearly we can see that this is just n plus 1 squared. And look, it holds. We just prove using the inductive hypothesis in here that our sum is equal to n plus 1 squared. It means that phi of n plus 1, this one in here, holds. And it holds for all the cases of n, when n is equal to 0 and when n is greater or equal than 1. We prove by mathematical induction principle, the MIP. This is the conclusion of our proof.